is the book. Each one has one. So if you go to the book, and to get to the different menus up here, you can't tab or move. You have to tab. I'm sorry, I said that wrong. You have to press 1, 2, 3, 4, and so forth. You have a repeat of the symbols palette and the template palette and other things in here. But go to the number 1. Now these are alphabetically every function that's in this Inspire. And there's some things that are located other places, like in the menus. Some of these are not. And this one is located, and I believe, I know it's in the number. If you go to menu, let me just show you this. You don't need to follow me. If I go in a calculator page, okay, so I'm going to go to a calculator page, and I go to number. There it is, number tools. We're going to do what's called floor. Now you really don't want to have to get in and out of a graphing page like that. And so here's what we can do instead. I'm going to go back to that graphing page you see. This is where we use the catalog. Again, the alternative is to open up a calculator page and try to do some work that way. But you can do the same thing here. Is everyone with number 1 here? On that, press number 1 if it's not. And get this open. Okay, all you have to do is find the letter F. The function is called floor, and we'll talk about why it's floor and not ceiling here in just a minute. And then just scroll down until you get the word floor. When you're down there, press enter. Now, could you just type the word floor? Yes, you can. You can just type the word floor. Now, why would the greatest integer function be floor and not ceiling? Yeah, so if you think about this, the floor is the low value, okay? So now if you had a function, and there are functions where you take the least integer that is not less than, then you'd have the ceiling. So our greatest integer function is the floor. So if you know that, then this problem is going to be, we'll insert 1 minus, so we can go in and we're just going to look at the function f of x here. So when we have f2 of x, we're going to say f2 of x equals, and we're just going to have this piece right here. Don't put limit in. Limit is asking for a single value, and we don't want that. So let's see, we've got the floor, and we're going to put in 1, hang on a second. We need 1 minus that, don't we? Okay? 1 minus the floor, 1 minus the floor, and now we're going to put in a fraction. And we're going to put in the opposite of x divided by 2. We're just putting in that function, nothing else. So 1 minus the floor. Now, if I'm going to be approaching 1 from both sides, if I put, let me go back to the notes here. If I put in, let's say, x equals, let's see, a value less than, we'll let x approach 1 from the less than. I could put in 0.9, 9/10. Okay, so I have here then 1 minus the greatest integer that does not exceed negative 9/10 divided by 2. Well, let's see, if I have 9/10 and I divide by 2, that's the same as multiplying by a half. So that would be negative 9/20. So what's the greatest integer that does not exceed negative 9/20? Should be negative 1. So now if I take 1 minus a negative 1, So this would be 1 minus, and now my value here is -1. My answer should be 2. Should be 2. Okay. If I have x equaling 9/100ths, I'd have 1 minus the -9/100ths divided by 2. Let's see. That's equivalent to, well, let's see. 9/100ths, -9/100ths divided by 2 is that. And so I'd end up with -9/200ths, which again is going to be -1, which is again is going to be 1 minus a -1 or 2. Should be. Let us see if that happens. Press enter. So I'm approaching 1 from the less than 1 side. What are my output values? 2. Okay. So it works. It works, in other words. So that's the type of thing. Now the only reason I want to bring that to you is because we don't deal with the greatest integer function that much. And if you have some of those, I want you to know how to do that. So on your Inspires, you use what command to get the greatest integer function? 4. Okay. There you go. Okay. Oh, let's see. The existence of a limit. Here's our theorem now. Let f be a function, and let c and l be real numbers. Let's just do a little bit of review here. What does c represent and what do l represent? C represents what part of the function? Input or output? Input. And L represents an output. Okay, so let f be a function and let c and l be real numbers. And the limit of f as x, oops, this broke. I'm sorry, this broke the line here. At least get in these notes. There we go. There we go. That looks more like it's supposed to. The limit of f of x as x approaches c is L. That's our typical definition. If and only if. Okay, now what does this mean to you? What does that mean to you? If and only if, IFF, if and only if, what? What does this represent? As you approach it from the less than c side, so if you approach it from the less than side, your limit is L. What's this mean? Don't say positive, but say greater than. Because if we're in negative values, you have to be careful with that then. Okay? But the greater than side, then the outputs are also going to L. Have we talked about this in class before this theorem came up? The limit only exists if the one-sided limits are the same. Okay? If and only if the one-sided limits are also equal to L. Okay? They say the same thing. As I come up from the less than side, come up from the greater than side, am I going to the same value? Yes. Therefore, the limit exists. Okay. Inherent in our limit notation is that both one-sided limits are doing the same thing. Otherwise, we can't clap. Okay? If I come up to this side here and I come up to this side here, I can't clap, and so therefore this would be a situation where the limit does not exist because we have two different one-sided limits. Okay, let's see here. Definition of continuity on a closed interval. Now, on a closed interval, what we're saying is, okay, what we're saying is, again, these brackets mean that we have a less than or equal to, not just less than, and x, the input, and less than or equal to, and then the other quantity there. As opposed to this, which is saying that we have A is less than X is less than B. So be real careful when you read these. If it says interval, it's going to look like a pair of numbers, coordinates of a point. But if it says interval, you need to understand that it's open, meaning that we don't include the endpoints. Okay, a function is continuous on the closed interval if it's continuous on the open. Okay, so without the endpoints, is it continuous? If it is, then it's continuous on the closed one, because all we're missing are the endpoints. If the limit as we approach this endpoint from the greater than side is f of a, and if the limit as we approach this side of the interval from this direction, the less than, is equal to f of b. Now remember, in our original conditions for continuity, we say that the limit exists, and if we have a closed interval and we can't get past A and we can't get past B, we don't have the ability to go from both sides. And so we have to have this statement to say, it's still going to be considered continuous on the closed interval, even though I can't speak the word limit in the truest sense, because I can't come from both sides. If, as I approach it from the the greater than A side, I get f of A, and from the less than B side, I get f of B. Okay? If it's continuous in between A and B, and we then have A included and it's the same value, and B included. What it's saying is this: you can't have, if this is A and this is B, and let's say that it's continuous here, okay, it's on a closed interval. What would happen? Would we still say that it's continuous if that happened? And that's what it's trying to say. This would be one that's not continuous because f of the limit as we approach A from this direction isn't the same thing as f of A. So it's just guaranteeing that we don't have this situation happening. Okay, I'm going to put this in red so that we understand that that's a non-example, an unexample of this. Okay. Oh, let's see. Here we go again. We had these for limits. We now have them for continuity. What we're saying is, if B is a real number and f and g are continuous, these are functions continuous at C, so we know continuity exists for these two functions. Then what happens if you have a scalar multiplied to all the outputs? Is it still continuous? Yes. What if we have those two functions added together? Is it still continuous? And the answer is yes. The outputs of one add to the outputs of the other. It's still continuous. If they're continuous individually, they're continuous when we add them, multiply them, and divide them. Of course, being careful that our denominators are not equal to 0 in any case. Okay? So here we go again. These are the same properties that we see over and over. We saw them for limits, scalar, sum and difference, product and quotient. We see them now for continuity. Continuity is guaranteed even if we do these operations. Okay. We better stop.